Hey everybody, this is a problem in which we find the work done by an object that is swung around on a rope or a tether, the work done against gravity. So let's get into it. A 0.625 kilogram tether ball hangs from a 3.60 meter rope. It is punched and swings in an arc up to an angle of 97.0 degrees from the vertical. How much work was done against gravity to get it to this position? So let's just start with a diagram so we can get our bearings straight. It is fixed to a rope and it starts out hanging vertically. And the length of that rope, I'm going to call L, is 3.60 meters. That's capital L. And it is knocked up, punched, and it swings in an arc, not a perfect arc, up to an angle of 97 degrees. So 90 degrees would be right here, and we know it's past that, and so it's going to be 7 degrees past that. So it's going to swing up somewhere around here. It's not going to be to scale, but we know it swings up that high. And this angle right here is going to be 7 degrees, right here. So we need to find how much work was done against gravity. And the key to figuring this out is realizing that the work done against gravity is always going to be equal to the change in potential energy. So it's going to be mg times delta H. We know the mass, we know g, so all we really need to do is find the change in height of our object. So let's start filling in our diagram a little bit more so we can find the change in height. Well, we know it starts out here and it goes up this much to reach that 90-degree mark, but that's just the length of the rope. That's 3.60 meters. If we want to find the total change in height, we also need to find this little bit, which I'm going to call delta H. Well, no, not delta H. Let's call it H2. I'm going to call this H1. We also know that since it's attached to this rope, we know the length of the rope is still L, equals 3.60 meters. And you might notice that this forms a right triangle right here. So we're actually just going to be finding the vertical component of this string length, H2. So let's use trig to figure out what H2 is. Since it is opposite our angle, 7 degrees, we're going to be using sine. So H2 is going to be equal to L, or 3.60 meters, times sine of theta, which is 7 degrees, 7.0 degrees. We plug that into a calculator. We get 3.60 times sine of 7 degrees, 0.439 meters. So H2 is 0.439 meters. Our total delta H then, change in height from beginning to end, delta H is equal to H1 plus H2. So that's 3.60 meters. This H1 height plus H2, 0.439 meters. We add them to get 4.04 meters. So delta H. Then to find our work done against gravity, it's just mg delta H, which is 0.625 kilograms times 9.81 meters per second squared times 4.04 meters. Our work done against gravity is then 24.8 joules. In summary, to find the work done against gravity, we just need the change in potential and energy, gravitational potential energy, mg delta H. So we need to find the change in height and the weight. We use geometry to find the change in height, and we're given the mass so we can get the weight. Hope that was helpful. Bye.